Okay, let's learn about temperature inversions and see what the heck they have to do with air pollution. You might guess by looking at this picture, they have something to do with it. Wow, that's an awesome picture. Okay, so under normal conditions, as we talked about before in our unit on the atmosphere, as we go up in altitude, we expect adiabatic cooling to occur. And what that means is as I go up in altitude, the temperature drops within the troposphere. So as I go up, for every kilometer I go up, there's about a 7 degrees Celsius drop in temperature. This is called adiabatic cooling, and it basically is just the result of decompressing air. So basically, as the pressure goes down, the temperature goes down. You may have noticed this if you've ever had like a spray can of some kind, or maybe you had an opportunity to play paintball. But if you start off with a container that has a high pressurized gas in it, and you let that gas out, over time you'll notice it gets cooled. Like you could take a balloon and do this. If you blow a balloon up and hold it, as the air inside the balloon becomes decompressed, it cools off. That's basically called adiabatic cooling, and this is what normally happens. Except sometimes it doesn't happen. And that's when we have what's called a thermal or temperature inversion. In a thermal inversion, which is also called a temperature inversion, instead what happens is there's this layer of warm air that forms. It's not that there's really warm air above the ground. What happens is the air near the ground gets colder than normal. So essentially, as we go up, we get to a point where instead of it cooling down, it warms up. And when that happens, we call this region here an inversion. And inversions are important because they prevent the upward movement of particles in the atmosphere, and that prevents pollution from dissipating like this. So under normal conditions, as I go up, I go from warm air to cooler air to colder air. That's just normal. It's adiabatic cooling, 7 degrees per kilometer. And what this does is it allows air to just decompress normally. And as it does that, it carries pollutants with it and it disperses them. Now, we shouldn't be making these pollutants, but the biggest health problems occur in cities where these things become highly concentrated and cause health problems. If they were to dissipate, they would be less problematic to human health. But what happens in an inversion is I have this warm air above. So instead of it cooling constantly, I have cooler air, then I get warm air, and then I get the cold air. And so what happens is air can't rise above this. If the air here is cooler than the air here, it's not going to rise above it. It's going to be trapped. So it's just like having a warm layer of water on the top layer of, say, a pond. And so what happens is the air gets trapped within here, and the smog levels can really build up quite high. So this is called a temperature inversion or a thermal inversion, and they have some pretty significant consequences on air quality in cities. And I think I just told you this, so I don't need to go any further with this. So there's three ways in which these temperature inversions occur. One is called radiation inversion. Don't worry, it's not as scary as it sounds. There's subsidence inversions and there's frontal inversions. Let's look at each of those. Let's start with the most common kind, and the kind that you can see quite frequently right here in our area. So a radiation inversion works this way. By radiation, the radiation we're talking about is infrared radiation, the thing you and I give off. All objects that are warm give off, well, all objects at any temperature give off radiation. Objects that are about the temperature of you, me, or the Earth give off infrared radiation. That's what is detected by the little cameras as we walk into KIS each morning. Well, what happens is, remember, first law of thermodynamics, if energy leaves the ground at night, let's say in the form of infrared light, then there's less energy left in the ground. So what happens? The ground gets colder. So what we find is this. On clear nights, when the air is still, well, regardless of whether air is still or not, on clear nights, what's happening is this radiation, this infrared radiation goes into space and causes the ground to get cool. But when the air is very still, what happens is you're able to build up this cold layer next to the ground, because as the ground gets cold from giving off radiation, then the air next to the ground gets cold. And this layer can get to be about 0.5 kilometer deep. All right. So we end up with this layer of cold air near the ground, and that's what makes a thermal inversion. So what happens is if there was clouds, then what would happen is the infrared light would get stuck and it wouldn't be able to escape, and the ground wouldn't get that cold. So it only happens on clear nights. On cloudy nights, we don't get thermal inversions, at least not radiative ones. But on clear nights, we do, because the infrared light can't escape into space without being captured and re-radiated by water vapor in clouds. So what happens is we wake up in the morning and we've got a scene on our hands. What happens is there's cold air down below and warm air up above. See, what happens is instead of it cooling all the way up like this, it cools and then it warms and then it cools. And so we get this layer here, this cold layer, and you can often see it very clearly. There's just this boundary above a city. You can see smoke going up and just hitting this layer right here. And it's like it hits the ceiling and it gets trapped under there. And as the morning progresses, the air gets more and more and more unhealthy. Now, when do these things form? Well, as the sun sinks in the sky, the ground is warm and it starts. The ground is already radiating off, but radiating. It's always radiating off. It's always giving off infrared radiation. But as the sun starts sinking down the sky towards sunset, then we're getting in less energy from the sun, and then the Earth is getting rid of more energy than it's gaining from the sun. And if the ground is giving off more radiant energy than it's absorbing from the sun, it's going to start cooling off. This starts happening about 2 to 3 hours before sunset. And it continues all through the night as long as it's a clear night. Remember, clouds will block that radiation and direct it back to the ground. And then what happens by sunrise, the layer of this cold layer will be at its thickest. And then as the sun comes up, it comes down, it warms the ground. As it warms the ground, then what happens is this layer warms up. And as soon as we have a situation where this air here is warmer than this air here, it just dissipates. But in the meantime, we're breathing this awful air. Now, another thing that can happen is that cloud cover can come in and we can be stuck with this sometimes for significant periods of time. Now, because the air in these radiation inversions is fairly cold, we often can get fog associated with them. And it's kind of weird. There's sometimes I don't know if you ever had this, like, is this foggy or is this pollution? Well, often the answer is both. It's fog because it's below what's called the dew point, the temperature at which water vapor condenses. But it's also polluted because the pollution can't dissipate the way it normally would. It's like being in a garage with the car on. The pollution can't go anywhere. It just builds up to these horrible levels. And it can be horrible. Just when you see pictures of really, really bad pollution, it's usually taken during an inversion because the pollution just gets stuck at this low level. Now, these radiation inversions are most common in the winter months when the ground is cooler, and in the early spring. In Korea, that's when we notice them the most. So as we start moving into winter and into early spring, you'll notice we'll start getting some pretty lousy air quality. Quite often it's because of these inversions forming. And we often have still clear air at that time of year. Now there's another kind I want to talk about. This one's a little bit trickier to get your head around, but it's called a subsidence inversion, or a subsidence, however you want to say it. And basically what happens is, you've probably heard of high pressure and low pressure air masses. When a high pressure air mass moves in over a region, like I live in the Seattle area when I'm not in Korea, and we get these in the summertime, not in the wintertime. In the summertime, we tend to get these high pressure ridges that form. Well, what happens is high pressure is mostly air coming down. If you recall, when we talked about the global wind patterns, descending air is high pressure. Well, as this air descends, it's the opposite of ascending air. Remember, as air ascends, it decompresses and cools down. Well, as air as air comes down, it compresses and warms up. So we find is, and I wish this showed it a little bit differently, the air is really being compressed inward as it comes down, and that heats it up. And so what happens is we get this layer of warm air forming above the ground, not because the ground cooled down, but because the air that was descending heated up. And then it got to where it was so warm it couldn't get through this colder air below. Now these things are really nasty because these high pressure systems, they can last for weeks. As I said, in Seattle, I live across from Seattle. We usually have just gorgeous air. If you look at the AQI map of the world, we have some enviable air. Our AQI is usually single digit. Well, what happens though is in the summertime, oh, it's beautiful. You can see the mountains. It's just so gorgeous. The sky's so blue. And the next day, not so much. And as the days go on and the weeks go on, the air is just rotten. And it's just because we have this big layer of warm air that's being established by the descending air heating up and forming essentially a cap over the city. So there's a couple ways of thinking of this, and a couple of famous examples. Famous example one would be Los Angeles or other places on the coast. What happens is at certain times of the year, you have mountains here, you have the coast here. What happens is as as prevailing winds push air out of, in the case of Southern California, the high deserts, as the prevailing winds push the air over here, it gets compressed, and then as it sinks down, it gets compressed even more. So as the air comes down, it's compressed and warmed, and so you get this warm layer. Now in LA is compounded by the fact that the Pacific Ocean is there and it's cold, and so you have the ocean which has upwelling, which is cold. So you have the water cooling the air, keeping it cool, and then the compression of the air coming over the mountains is warm, and so they can get these prolonged. As long as this wind system is here, and as long as the ocean is there, they can get these really really lasting inversions, which can make their air really miserable. I mean, the first time I took my kids to Disneyland, I only took them twice, but the first time I took them there, this is what I saw, and I was like, "Oh my God, I'm bringing my kids into this cauldron of pollution. What am I doing?" Of course, we had a great time when we got to Disneyland. You know, if you've never been, you got to go to Disneyland. It's really fun. Okay. Uh, Another way it happens, another famous example is the city of Denver, Colorado. And this happens in a lot of places. This happens in India. So what happens is when you have cities that are in valleys, this can be a problem for inversions, because what happens is as the wind pushes air up over the mountains, it'll come down the other side. And remember, as it comes down, descending air compresses and it heats. Just as rising air expands and cools, air that's falling down compresses and heats up, and you'll get this layer of cool air trapped in here. Compound that with the fact that up here at night, for instance, when the temperature cools off, this cold air is dense, and so it runs downhill and it tends to fill the valleys. So the valleys tend to fill with cold air coming down from above, and they get capped off by this inversion layer that forms when the air gets compressed as it comes over mountains. And this is something that happens in Denver, Colorado, which, it should have gorgeous air, but they often have really terrible air because the wind is often westerlies, the prevailing westerlies. The air is coming over the Rocky Mountains, and as it descends, it compresses, and it makes this layer that you just sit over Denver, Colorado for weeks and weeks at a time. And the last time we'll talk about is called a frontal inversion. I don't know if you listen to the weather at all. I mean, when I was a kid, it used to be on the news a lot, but you don't get your news that way. They talk about air masses. Like, oh, we've got cold air mass moving in from Michigan. Okay, well, what that means is you have cold air masses and warm air masses. And when a cold air mass pushes itself underneath a warm air mass, then what happens is as this moves this way, kind of move this. So there you can see. Okay, as this cold air moves this way, it is pushing itself underneath this warm air that was over here, and so you end up with cold air down below, and so you'll get an inversion. Now these inversions are not quite as bad for two reasons. One, these air masses are forming this because they're in motion. I mean, you can get a stalled air mass, that's true. But the other thing is, if you look at it, they're not flat. They tend to be angled, and because they're angled, then this pollution has a tendency to spill upwards. So these are really less problematic. Okay, so that's inversions for you. I don't think I have any more slides for you. No. Okay. Thanks for watching, and just please take this information, process it, write down what you need to, and be ready for the test. See you later.